I'm sorry, change the growth factor a little bit. It's not so bad. So which of those should we start with by looking at? What do you think? If you want to pick one. Yeah, on the homework. Fiona, what was the one that gave you a goofy number with an E on the calculator you didn't think it was right?
I think it was
16? Oh, Ashley depositing $3,400? Okay, so she deposits $3,400 in an account with an annual yield of 5%. So here's what I'm going to ask you. Which equation did you use?
in my calculator I did the 3,400 times 0.05 with the up thing and then 8.
Okay, so you did 3,000, how much is it? 400 times
0.05.
and then to the
8.
8th? Okay, so this is number 16, where they're taking $3,400 and they're investing it at 5% growth. So this represents the beginning amount, the principal. This represents 5%. So if you think of this, we're taking 5% of this number if you multiply it one time. So we're taking a small amount of this. You know, 5% is only 5 over 100, which is 1/20th. So you're taking 1/20th of that money. And then you're taking 1/20th of the answer in 1/20th and 1/20th. So you're taking $3,400, you're taking a little amount and a really little amount. That's what that is doing. But you want to make it bigger, right? Because this is interest. So there's something missing from this. The one, yeah. So you need to have $3,400 times the money, and then you take that times the 0.05. So you take all of that money. So what we want to do is we want to rewrite this. The equation looked like that. That 1 is the 1 times the money, and then this is the interest times the money, and you add them together. So you start out with a pile of money, and then you put some interest on top of it. And then you take that amount of money, and you put some interest on top of it, and it keeps growing. This here takes an amount of money, and it cuts it down. And then it takes that amount, and it makes it smaller and smaller. So you're just missing one piece to this. So if we write 3,400 times 1 plus 0.05, put that in your calculator, and then you're going to have it. That is going to give you some total amount of money after 8 years getting 5% interest. Got it? What did it come out to? Somebody must have it.
So it's $5,023.35.
$5,023.35. Okay, that makes more sense. See, I think what you had when you did this is you ended up with an e to a negative power of 10, an extremely tiny number, which you're right, that doesn't make sense. So the answers, what does the answer tell us? Okay, so, oh, I'm sorry, I'm reading another problem. Okay, skip that. So what other problems in this? 11? So it says, considering the exponential growth model for California's population. So California's population must have started at 5.68 something. Is this millions? Is that right?
Yeah.
And then the 1.29 is the growth factor. So if you think of 1.29 as a percent, that's equal to 129%. So in other words, California's population is growing, according to this model. And each year, it's 129% of the previous year. So for every 100 people, there's 129 people next year. So that's the model. And they say, how much does the model's value for 1999 deviate from the actual population? Okay, so this, we have to look back. And we have to look at that graph on page 407. Did you do that? Look at page 407 with me, or else you won't understand what we're doing. There's the graph of California, and this is decades after 1930. So this population here is the population in 1930. This is the number of decades after 1930. So we're asking, what is the population in 1990, right? Is that correct? Is that what they're saying in the question? So if something deviates, what do they mean by that? Hmm?
How far away?
How far away, yeah, the change of how far it is away from the actual population. So on this page 407, what's the 1990 population?
76,000.
Okay, so if we look at the graph, it's at 29.76, so that's in millions. So in 1990, it's 29.76, and that's millions. And this is in millions, so if we do the arithmetic with this equation, we want to compare that number to what the actual was. This is the predicted. So we say 5.68 multiplied by 1.29, and how many decades is 1990 later than 1930?
6.
So we put a 6 in there. And you push that through your calculator. What does the calculator give?
Gives
Show your calculator out. That should be like your third arm right now.
6 million.
5.68 times 1.29 raised to the 6th power. Round it off. 26.2? Good enough. Well, there's 2 place values there, but that's good enough. So all you do is you subtract. So they're off by about 3.5 million. So the model shows that it should have only been this high, but it was actually 3.5 million higher. So California was growing even faster by 1990 than what they thought it would. California's got big issues with people, because they have more people than they have space in their cities, and more people than water. Big problems. So with climate change, when the weather changes, their water supplies change. They go from extremes. Way too much rain and not enough rain. And that's why you see those fires going on down there in parts of that state that have never burned in known history, like redwood forest and everything. It's all on the edge of burning up. And that climate, up until very recently, was much more like our climate. Pretty moist, relatively cool, just further down the coast. So, that's how you go after that one. Use the equation to get what the equation would predict. Use the measured value and compare. That's your deviation. What else? Do I do any more of these? 5 minutes, decay. Yeah, I should explain decay to you. I think I can do it in a couple of minutes, give you at least an idea what we're talking about with decay. So, if we started with a number like 10, and we lost 10% every single day. So let's say that this is students in class. When COVID hits, we lose 10% a day. How many are you gonna have after one day? You're gonna be down to 9, yeah. This is gonna be kinda hard because we're gonna end up with partial students, aren't we? That's all right. How many are you gonna have after 2 days? Now we're gonna lose 10% of 9. So this is days and this is people. After 0 days, we have 10 people. After 1 day, we're down to 9. After 2 days, we're gonna lose 10% of this. What's 10% of 9? If you gotta do that, do it. What is 10% of 9?
No, I don't know how to do that.
Oh. We're gonna subtract 10%, yes? Okay, how do you write 10% as a decimal? 0.1. We're not gonna subtract 0.1. We're gonna subtract 0.1 times 9. So we're gonna subtract 0.1 multiplied by 9, which is a negative 0.9. So now we're down to 8.1 people. So after 2, we didn't drop a whole 1 though, did we? We only dropped 9/10. So the change is dropping 1, and then the change is dropping 10% of that number. So now what's gonna happen after 3 days? We're gonna lose 10% of 8.1. So we're gonna lose 10% of 8.1. How much is this? Remember all that multiplying and dividing by powers of 10 that we've done in the past? That's what's going on right here. This is like multiplying by 1/10. It's like dividing by 10. So your decimal point moves back. So 0.81. So I gotta subtract 0.81 from this. So that's gonna be 7 point, so you're gonna take 8.1 and subtract 0.81. What's 8.1 subtract 0.81? How much? 8.1 subtract 0.81. 8.1 subtract 0.81. 7 point, how much? 7.29. So this went down by 1, this went down by 0.9, this went down by 0.81, this is gonna go down by 0.729. So you see it's going down by less and less and less. So what ends up happening is you get a curve that goes down. Instead of, with this kind of thing, California's population is a curve going up. So how do we do the calculation? That's what we talk about tomorrow. We'll walk you through that tomorrow. The calculation is still going to use this. What's going to be different is what we call the growth factor, because it's not growing, it's decaying. So it'll make sense to us. We'll get through that tomorrow. So